Welcome back to mass transfer operations 2. We were discussing on liquid extraction. In the last class, we discussed the design calculation of single stage operation. Now, we will be discussing on design calculation of the multi-stage operation. This multi-stage extraction operations are of two types. One is this cross current extraction, another is counter current extraction. Firstly, we will be discussing on cross current extraction, and then we will be discussing the details of the counter current extraction. So, the multi-stage cross current extraction, the schematic of the extraction process is this, like say feed is entering in the first extraction unit, where this extracting solvent S1 is added with this solute concentration as Ys, and flow rate of the solvent is extracting solvent is S1, and flow rate of the feed is F1 with the solute concentration as Xf, and it is allowed to separate into two different parts. One is this, we can say this one extract, that is we can say this one E1 with Y1 solute concentration and raffinate as R1 X1. So, if we can imagine that the multi-stage cross current extraction processes are the summation of n number of single stage operation. The only difference is that the raffinate of the previous unit is the feed to the next unit, extraction unit. So, this is the only thing, and we can say this one solute concentration in the solvent is same for all these stages like this Ys, but we can say that solvent amount can be varied from S1 to S2 to S3 to like this Sn. Okay. And also we can keep the solvent concentration same also. We have this liberty to control everything. Okay. So, let us take the nth stage like this here, where we can say this one the feed is entering, that is we can say this one raffinate of the previous unit, like this we can say stage, that is R n minus 1, and the solute concentration is X n minus 1, and we are adding this solvent extracting solvent Sn, and the solute concentration in the extracting solvent as Ys. And whenever it will be exiting from this nth component, that we can say the raffinate flow rate will be Rn, and the solute concentration will be Xn, and the extract amount will be En, and the solute concentration will be Yn. So, now we will be doing this, we can say this one mass balance and component balance for stage n, say suppose for stage n, say total mass balance will be like this, say R n minus 1 plus S n, we can say this will be like M n, that is nothing but R n plus E n, and this mass balance of this we can say this one C, that is R n minus 1 X n minus 1 plus S n Y s is equal to M n X m plus is equal to R n X n plus E n Y n. If we know these say R n and S n and Y s, so we assume that these are known, then we will be able to get, then also this X n minus 1 also we will be able to get what is the value of R n and X n and E n and Y n. We assume that this nth stage is attained these equilibrium stages, and whenever the R n and E n these are separated, or we can say this one raffinate and extract phases are separated, then these are in equilibrium. So, we can say this one, whenever we will be getting this equilibrium relationship, then x n and y n these are in equilibrium. So, we can assume this one, okay. And say through this m n position, suppose in the say ternary diagram, whenever we will be getting this x m, that is from this we can say this mass balance and component balance will be getting x m, means that is the solute concentration in the mixture, that is we can say this fictitious one. Then so we will be getting this x m. From there, if we draw a tie line to this raffinate arm and extract arm, we will be getting this x n and y n. Okay. So, now we will be doing this step by step procedure for the we can say this one extraction efficiency, or we can say this one separation efficiency in the we can say multi-stage cross current extraction process. This is very simple or easy to understand this one. So, first step will be like this. Stage 1, we can say this one, whatever the stage 1 actually is there, suppose this stage 1, here we can say this one receives the fresh feed. Okay. So, we can say this first step will be like this stage 1, it receives, actually we can say this one receives fresh feed, and say it does not contain any extracting solvent. So, we assume this one it is no extracting solvent. So, here B is absent like this. Okay. So, now we will be putting this n is equal to 1, because you see this one n is the number of stages. So, in first stage we can say this n is equal to 1, then we can say this one mass balance and component balance will be like this R n minus 1, that is R 0 plus S 1 is equal to M 1 is equal to E 1 plus R 1. This R 0 is nothing but we can say this one is feed. So, we can say this one F plus S 1 is equal to we can say this one E 1 plus R 1. Okay. Now, you see we need to locate this feed point location, because it is finalized, or we can say this it is known to us, and we know this S 1, suppose this is S 1. So, we know this feed point location. So, it will be like this x b, that is why we told that no extracting solvent. So, x b is equal to 0, and we can say this one, this f x is suppose one value is there. So, for this x f we have this feed point location, and S 1 also we know this one, what is the composition of the S 1. So, we know this one, what is the x b value, that is almost around we can see this one 100%. So, near 1 actually it will be, and with some amount of the solute concentration, that is why it is not meeting this x c is equal to 0, some x c value will be there, because you see this one in most of the extraction processes we will see that the pure solvent, extracting solvent is not used. I told this one earlier also, that pure extracting solvent is not used for the extraction process. This solvent is already received from other extraction process. So, some amount of the solute may be present. If it is a 1-2% like this, then it is coming as at this say 1-2, due to this 1-2% it is not coming in the this one we can here. Okay. So, we will be getting x 1 like this, this S 1 will be placed here. Okay. So, now we have this one, this x m 1, actually we can say this one x m 1 will be getting from this component balance. So, we know this one x m value is known. So, we will be putting this x m value is equal to this one. So, in this f and S 1 line, so we will be locating this x m 1. Okay. So, x m 1 is now located in f S 1 line. Now, we told that this one, this whenever we have this one this M point, M1 point, or we can say this mixture point, and we allowed this mixture to be separated into raffinate and extract arm. So, that is in equilibrium. So, we can say this one, it will be separated into two parts, or we can say this one is this raffinate, another is extract. So, it follows this tie line value. So, now we have this R1 and we have this E1. So, in R1 and E1, what is the composition of the solute concentration of this one in the raffinate and extract? We will be getting, say, this one from this, we can say this one equilibrium diagram like this. This is the equilibrium line for this raffinate arm. So, this is, we can say this one equilibrium line for the extract arm. This is extract arm and this part is raffinate arm. So, we can say this one, we now have E1 and R1. Okay. So, if we now remember this one, that R1, that is the feed to this stage 2. So, we can say this one, we have now say for this second stage, we will be getting this one. So, for stage 2, we can say this one, R1 is feed. Okay. So, R1 is feed, and we know this one, say suppose this S2 is now known in the S2 like this. Here suppose this R1 is the feed and S2 we are adding this one. So, now we will be doing this one, S2 will be somewhere here also, suppose S2 is here like this. Now, again we will be adding this R1 and S2. So, now we need to join this one, we need to say, we need to first locate S2 and then add R1 S2. So, in between R1 and S2 we need to get, now we need to find point M2 from XM2, that is from this we can say this one component balance equation we will be getting M2, that is we can say this one, that is we can say this one, that XM2, like this is actually XM1. Okay. So, XM2 also here in the for the second stage, now again we are allowing this system to be separated into extract and raffinate. So, here also it will be like this, we are allowing this one to achieve the equilibrium, then they according to tie line with this mixture will be separated into two parts like this E2 and R2. So, now we have this R2. So, in the raffinate arm we have R2 and in the extract arm we are getting. So, now say we need to follow this tie line through M2. So, which is separated into we can say this one R2 and E2. Okay. So, now from R2 and E2 we will be again getting the solute concentration in the raffinate arm and the extract arm, and you see this one, this R2 is the feed to the stage 3 and we have this for the stage 3 we have S3. Suppose the S3 also is somewhere else like this, we can say this is S3. Now, R3 is the R2 is the feed to the third stage. So, what we will be doing now? We will be again adding this R2 and S3 for stage 3. So, now we will be writing for stage 3 we can say this one R2 is feed and locate S3 there. Suppose S3 will be placed somewhere else like this, say this is suppose S3 and now this is R2. Now, we need to join R2 and S3. So, we will be joining this R2 and S3. Okay. And we need to calculate XM3. So, this is nothing but this one. So, XM3 is like this. So, this is we can say this one XM3. Okay. and then we are now allowing this system to be separated into, we can say this one R3 and E3. So, we can say this is now, we can say this one separating into E3 and R3. Okay. So, this system actually will be going on, from there actually we will be getting whatever the composition of x3 and y3, like this for all the stages we will be getting this, all these x1, x2, y1, y2 and x3, y3. So, that way we will be getting all the solute compositions in the raffinate and extract arms. So, we will be continuing this one till the end, means how many number of stages are there, we will be getting this one and we will be moving like this. Now, R3 becomes the feed to the stage 4 and it will be continuing like this. So, if we add this R3 and S4, then there also we will be getting XM4, there actually then we will be getting this one, we will be allowing this to be separated into two this one streams like this raffinate and extract, and then from there, from the equilibrium data points, means equilibrium line, we will be getting what is the x3 and y3 values are, and also we will be getting the we can see this flow rate also. So, from the beginning we know feed rate, we know S1 means the extracting solvent amount in the stage 1, and we know that what is the solute composition in this feed and extracting solvent. From there we will be doing this one, from the equilibrium curve we will be getting what is the amount as well as this concentration of the solute in raffinate in extract, and accordingly in the from the stage 2 what is the amount of raffinate and amount of extract in the stage 2 as well as this composition. From this equilibrium line we will be getting both x and y values from this raffinate and extract arm. Okay. So, and we will be getting all these amount and composition of the extract and raffinate, and whenever we will be getting all these stages, we will be adding all these stages, means whatever the extract actually we are getting. Say if we see this one first, this one article schematic, you see E1, Y1, E2, Y2, E3, N3, like this one, the last one like this En, Yn, all these are added and then we will be getting one mixed extract. So, we can say this one total extract will be like this. So, this total extract will be E1 into Y1 plus E2 into Y2 plus E3 into Y3 and summation of this one up to En into Yn. So, this amount of the solute will be separated from the, see all the, we can see this whatever feed actually we have added and how many solvents actually are added in the different stages. Okay. And we again we are repeating this one, that for this extraction process, if the extracting solvent contains some amount of the solute, that is target component C, then whenever we will be calculating the efficiency, we need to subtract that solute concentration from the total extract and then we will be calculating the efficiency. Okay. Now, we will be say we will be solving one problem, the very simple problem actually, that say 1000 kg of an aqueous solution containing 35 mass percent of trimethylamine and 60 mass percent water is to be extracted using benzene as the solvent. So, here you see the water is A, the trimethylamine is we can say C and benzene is B. So, a 3 stage cross current extractor system is suggested. The amounts of solvents, we can say this one, that solvent is not pure one. Say 98% benzene is there and 2% trimethylamine is already present. That is why I told that in most of the extraction processes maybe 100% pure extracting solvent may not be used. If it is used, there is also no problem. Whenever we have this one, that S1, S2, S3 will not be sitting in this x axis, it will be due to this 1 to 3% C, it will be just above this, we can say this on x axis. And the solvent amounts are like in the first stage it is 815 kg, in the second stage we can say S2 is 950 kg and S3 is 2625 kg. So, here also one point we need to understand, that whenever we are moving from stage 1 to stage 2 to stage 3, we need to increase the amount of solvent, because you see in that case the driving force decreases. That is why we need more solvent to extract the dilutes, we can say this one feed, and that is why more solvent extracting solvents are required. Now, we need to determine the fraction of the solute removed if the stages are ideal, because you see we are now the assumption also is that say all the stages will attain the equilibrium, then only these will be separated into extract and raffinate this one phases, and that is why we say this one. Then x 1 will be in equilibrium with y 1, x 2 will be in equilibrium with y 2. So, that way the composition of the raffinate and extract as well as the tie line data are given below. So, like this in water rich phase we can say the feed, and then benzene rich phase is like this, we can say this one just after separation, we can say this one if it is in equilibrium, then only that type of say we can say this one water rich phase will be raffinate arm and benzene rich phase will be extract arm. We know this one because benzene we are adding there here to get this trimethylamine from this water to benzene, and tie line values also x c and y c, these are given. So, from here we can say this one for this first these two data sets we will be able to get. So, we can say this one raffinate, this is we can say this one raffinate arm, and this is say we can say this one extract arm, and these two are we can say this one tie line. So, this will be now putting this one in any of the say we can say in triangular diagram, maybe it is a right angle triangle, we are this one conversant with this right angular triangular diagram. So, we will start solving this problem like this one. So, this we can say this one raffinate arm is obtained using the first set of these data points, and extract arm actually are obtained for the second set of data points like this. And whatever the we can say this on dotted lines are there, actually these are we can say tie line values, and all other tie line values actually we may get using this one. These are also tie line values, and other tie line values actually we will be getting from the tie line data. If we can plot one x c versus y c in the right angle like this, you making one diagonal, from there we will be getting, or we can get this one using this conjugate line. Means say this one whatever the equilibrium this one tie line values are there from the equilibrium curve, we can make this one like this, making this parallel line and vertical line, from there we will be getting one conjugate line, from there also we will be able to get this other tie line values also for a particular mixture, because we do not know this where the xm1, xm2, xm3 will be there, that may not be falling in the tie line values. So, that is why we can get this one from any of these, we can using this conjugate line, or maybe we can use this one in the next say we can say this one we can plot one x c versus y c, from this we can equilibrium data point we will be able to get this one xm1, this xm2, and means the tie line through this xm1, tie line through xm2 and tie line through xm3 we will be getting. Okay. So, we will start solving this one. So, whatever the data points are there, first we will be writing those, okay. And then whatever the data points are not available, we will be getting from this equilibrium curve, we will be getting this very easily, and ultimately we will be adding all this one arms, 3 extra arms, and from there we will be deducting that whatever the contribution of the solute from the extracting solvents say S1, S2, S3, we will be deducting that part, and how much amount of the solute actually we can say this one trimethylamine is extracted, resultant amount divided by how much were there, how much amount of the trimethylamine was there in the feed. So, if we divide this one and multiply it by 100, then we will be getting what is the percentage extraction of the solute. Okay. So, we will be doing this one stage wise calculation very easily, we will be able to do this one. So, first stage 1 we will be starting with this stage 1. Okay. We have this feed is equal to we can say 1000 kg, and XF is given as 35% means say 0.35. Okay. So, that is now supplied, and YS actually is given as 0.02, 2% for all these, means say for y1, y2, y3 Ys is always, say we can say this one, Ys is fixed as 2% 0.02. So, that is already given. Okay. So, suppose y1 is 850 kg, suppose this y2 is equal to 815 kg, y2 is equal to 950 kg and y3 is equal to 2625 kg. Okay. So, we will be say now we will start with stage 1. So, here we have this one, we can say for stage 1 we have S1 is equal to 815 kg and say Ys is equal to say 0.002, this is common to everyone. So, now we can say F plus S1 is equal to M1 is equal to, we can say 1000 plus 815. So, this is, we can say this one 1815 kg. And now we will be finding this xm1 just from the component balance, we can say this one F xf plus S1 Ys divided by this mixture, say M1. So, it is coming out as, so 1000 into 0.35 plus 815 into 0.02 divided by 1815. So, it is coming out as, we can say this one 0.202. So, this is actually, we can say this 0.2, this is, we can say this one xm1 is coming out as this one. So, this is, we can say this one xm1. So, this is 0.202, just above this 0.2. So, now say we need to locate, say we need to first we need to locate say F, that is we can say this one, we know that F does not contain any extracting solvent. So, xb will be equal to, and say xb xc, that is xb will be equal to 0, xc is equal to 0.35. That is why it is 0.35. So, we know we can locate this feed point. Okay. And then again we need to locate S also or S1. So, this one first one will be like this, xb will be say 98%, means say xb and say xc, like this is actually say 98% 0.98 and this is xc is equal to 0.02. Okay. So, this is we can say, that is why it is coming here like this. S1 is this one, we can say we can get from around this xb is equal to 1 like this 0.98. Okay. Now, we need to join this F and S1. Okay. And we have this M1 also. Now, so this M1 or mixture 1 will be separated into two different parts like this R1 and U1. So, we can say this one now M1 will be converting into R1 plus U1. Okay. And we know this one, that M1 into xm1 is equal to R1 x1 and plus U1 into Y1. Okay. So, we now have this one. So, total mixture we know, total mixture is 1815. Now, you see from this equilibrium curve, so whenever this M1 will be converting into R1 and U1, it will be following this tie line. So, this is we can say this one tie line, because we assumed that the stage, all the stages this one attain the equilibrium. So, according to the equilibrium, it is converting into R1 and E1. Okay. So, now we can say this one M1 we know, xm1 actually we have got as 0.202 and then we have this x1 and y1 actually we know. Okay. We have this R1 is equal to 882.97 and x1 is equal to 0.24 and S2 is equal to 950 kg. So, we have this mixture is equal to 1832.97 kg and say if whenever we will be doing this component balance like m2 into x m2 is equal to, we can say r1 into x1 plus s2 into ys. So, here m2 is equal to 1832.97 into x m2 is equal to r1 is equal to 882.97 into x1 is equal to 0.24 plus s2 is equal to 950 into s2 is equal to 0.02. So, from here actually we will be getting x m2 that is equal to say 0.126. So, now this x m2 is equal to, we can see this, that is x m2 that is 0.126, actually we have got this one. R1 and S we have, and we have joined this one, and now from this x m2 we will be getting this m2 value, that is we can say this one using this x m2 is equal to 0.126. So, we have got this one, that m2, and through m2 now we will be drawing this r2 and e2. Okay. This we can say this one will be getting r2 and e2. Okay. And from there actually we will be getting now this x2 that will be equal to 0.15 and say y2 we will be getting as 0.105. Okay. So, we will be getting this x2 and y2 values, and then we will be doing this one, we will be doing again the component balance using this one, like we can say m2 x m2 is equal to r2 x2 plus e2 y2. Okay. So, we have this m2, we have this 1832.97 and x m2 we have found out that 0.126, that is equal to, we can say this one r2 that is unknown to us, we will be getting this one into x2 we have this one 0.15 plus E2 will be like this, the total is 1832.97. So, we can say this one 1832.97 minus R2 into Y2 is equal to 0.105 into say 0.105. So, from here actually we will be getting R2 that is equal to, we will be getting this 855.39 kg. So, it is R2 is equal to 855.39 kg. Okay. Then we will be getting E2 is equal to, say from this total 1832.97 minus 855.39, that is coming out as 977.58 kg. Okay. So, this M2 we can say this one, whatever the R2 we have, this one now is the feed to stage 3. So, we can again now for stage 3 we will be joining this S and R2. So, we will be for stage 3 we can say, for stage 3 we can say this one, it receives R2. Okay. So, that is we have this one 855.39 kg and S3 that is given in the problem, that is equal to 2625 kg. Okay. That is equal to say whatever we got this one 855.39 kg and S3 is equal to this one. So, now from this we can say whenever we will be doing this component balance for this system R3 is say R2 and S, and say we will be getting this M3, that how we will be getting this one, just by doing the component balance M3, that is we can say this mixture, that will be the summation of R2 and S3. So, that is M3, XM3 we need to get is equal to we can say R2 and into X2 plus we can say this one S3 and Y3. Okay. So, M3 that is nothing but the we can say this one summation of these two R2 and S3, that is coming out as 3480.39 into XM3 is equal to R2 is equal to this 855.39 into X2 is equal to that is 0.15 plus S3 is equal to 2625, and the solute concentration in the extracting solvent is already given as 2%. So, it is 0.02. So, from here actually we will be getting XM3 is equal to say 0.052. So, whenever we have this got this XM3 like this one, XM3 point, that is 0.052. So, now we have this point M3. So, we have this R2 and S and we have XM3. So, if we extend this one from this, we can say XC and YC axis. So, when it touches this R2S axis, from there we will be getting the point M3. Okay. So, here also this point in this mixture, this M3, it will be divided into two different parts, like this one will be R3 and another will be E3. So, from here actually we can say this one, if we read this one from R3 and E3, so we will be getting say we can say X3 and Y3. So, that we will be getting from this graph X3, that is obtained as very small value like this 0.06 this value, and Y3 that is again lower, that is we can say 0.051. Okay. So, X3 and Y3 we have, R3 will be getting from there. Okay. So, we will be doing this say component balance like this M3 into say we can see this XM3 is equal to, we have this R3 into X3 plus E3 into Y3. Okay. So, now M3 we have this one, already we have this one say 3480.39 into XM3, actually we have got this one as 0.052, that is equal to R3 we need to find out, R3 into X3 we have got is very small value 0.06. So, we can say, and this E3 means nothing but this total minus R3, that is 3480.39 minus R3 into say 0.05. So, from here actually we will be getting R3 is equal to, we will be getting by this manipulating this equation, we will be getting this 541.39 kg, and say E3 will be getting as say the rest of this means 3480.39 minus 541.39, that is coming out as 2939 kg. Okay. So, now we have this total x1, x2. So, we have this one x1, y1, x2, y2, x3 and y3, and r1, r2, r3, e1, e2, e3. So, we have all these parameters like this, and also we have m1, m2 and m3 means xm1, xm2, xm3. So, we have now everything with us, and also we know that the total amount of extracting solvent, how much amount of solvent is added there, and how much amount of the component say trimethylamine, that is also entered inside this extracting system. So, we know that also. So, now we will be finding that how much amount of we can say this one trimethylamine, that is leaving the stages means from the different stages like this. So, we can see this one total amount of trimethylamine, that is leaving the 3 stages will be equal to, we can say this one E1 say Y1 plus E2 Y2 plus E3 Y3. So, that will be equal to, we can say this one, E1 is equal to say 932.03 into 0.166 plus E2 is equal to 977.58 into 0.105 plus E3, whatever we got this one 2939 and Y3 is equal to 0.05. Okay. So, that this total amount is coming out as 407.3 kg. Okay. So, we can say this one, this is one point. Now, so how much amount of trimethylamine is entering inside the 3 extractors with the extracting solvent. So, that is also we need to consider, but whenever we will be calculating the extraction efficiency, we need to deduct that amount from the total amount of this one trimethylamine that is leaving. From there we need to deduct that amount. So, total amount of trimethylamine, so we can see this one entering. So, with solvent, so there are 3 different solvent. So, we can say this one will be equal to, can say S1 plus S2 plus S3 into, we can say this one YS, because for all the cases the solvent solute concentration in the solvent is same. So, it will be like this. So, we have this that these are given 815 in the problem, these are given S1 is 815, S2 is 950 and S3 that is given as 2625 kg, and the concentration of the solute in the this one extracting solvent is 2%. So, 0.02 kg. So, we can say this one, this amount we can say this one, this small amount, that is 87.5 kg, this one what is called trimethylamine has entered. But we say we have seen that total 407.3 kg trimethylamine is extracted. So, we can see the effectively we can see this one. So, now we can see this one net amount of trimethylamine, that is we can say this one removal. So, will be equal to, we can say this one 407.3 minus 87.5 kg. So, that is coming out as 319.5 kg. Okay. So, we can say this one. Now, how much amount of the trimethylamine was there in the total feed? So, we can say this one, we had 1000 kg feed. So, we can say this one total amount of, we can say total amount of trimethylamine. So, we can say this one in the feed. So, that is we can say is equal to, we can say this one 35%. So, this is 0.35 into 1000 kg. So, we can that is 350 kg. So, out of this 350 kg, now we have this one. So, we can say this one 319.5 kg, we can these are separated. So, we can say this one fractional say trimethylamine removal. So, will be like this 319.5 divided by 350 into 100 percentage. So, that is coming out as 91.3%. So, we can say this is the fractional trimethylamine removal. Okay. So, 91.3% trimethylamine is removed. Okay. So, that was the question for this problem. Okay. Now, we will be discussing about the continuous countercurrent multistage extraction process. So, in this case actually the feed is entering from one side of this, we can say system, and with say suppose feed flow rate is F and with the solute concentration as X F, and the raffinate is exiting from the other side of this, we can say this one extraction unit. So, that is we can say this solute concentration as X n and flow rate of the raffinate is R n. And in that side we can say this one, from where the raffinate last raffinate actually is exiting, there the solvent actually is added. So, that with the solvent flow rate is S and solute concentration as Y s. That Y s may be 0 in some cases, then that is why it is counter currently these are flowing. So, we can say this one, the extracting solvent will flow in this direction, and the ultimately the final extract will be leaving from the first extraction stage, where the feed was added, and the feed will be this moving in this direction like this. Whatever we have this one tried in this counter current cross current extraction, here we say both the extract and raffinates are moving in the cross current direction, and say this counter current direction, but the thing is that the solvent is not added in all the stages individually. So, solvent is added in the last stage of the extraction unit. So, we can say this on a nth stage solvent is added, and this solvent actually is carried forward. So, we can say this one extract and raffinate stream flow from the stage to stage in the counter current mode and provide two final products, like we can say this raffinate that is exiting from the final stage of the extraction unit, and extract that is coming from the first stage of the extraction unit. So, for a given degree of separation, we can say this one, this type of operation requires this less number of stages for the given amount of solvent, or we can say this one, this less solvent, we can say this one, say less solvent for a fixed number of, we can say stages than cross current method like this, whatever we have discussed previously. So, compared to this cross current extraction process, the counter current extraction process is, we can say, the economic. Okay. So, like this one here we will be discussing the step by step procedure also for the design of the multi-stage counter current extraction process. Before that, we need to understand the, we can say, process. So, in that case also, so we have this, we can say this binary zone like this is the raffinate arm, and suppose tile the plate point is somewhere here, and then this is the extract arm. Okay. And say it is, we can right angle triangular diagram. Now, we can say this we will be doing for the entire plant like this, the for the entire system. Say we can say this one, the feed is entering at the first stage and raffinate is exiting from the last stage, where this in the last stage say solvent is added, and from the first stage extract is this one taken out. So, we will be what we will be doing this one, if we do the material balance, then we can say this one F x f plus S y s is equal to, we can say this M x m, that is nothing but this E 1 y 1 plus R n x n. So, that is we can say this one, this whatever this in the first stage, that is x f, that is S y s in the last stage, and then we can say this one extract is coming out from the first stage with E 1 y 1, and raffinate is exiting from the last stage, that is with the solute amount will be R n into x n. So, whenever we will be doing this, suppose if we say this one E 1 minus f means in any of the stages, if we say what is the resultant of the flow rate, then that is nothing but we can say this one E 1 minus f, that is then in case of this we can say S minus R n. So, we will be getting always the common factor like this. So, that we now design, or we can say this one as the delta. So, this is nothing but the delta is a stream that obtained by removing a mass F of the feed from the first stage and this extract E 1, or by removing we can say this one mass R n of the last stage raffinate from the solvent S. or we can see this one in any stage. If we say this one, whatever is entering and what is exiting, what is the resultant of this one. So, we can say this one, if we do the now do the material balance in the envelope 2 like this, in the small envelope like this. So, there actually we will be getting like this R n minus 1 plus S is equal to R n plus E n. So, from here also we will be getting extract minus raffinate, that will be giving like this S minus R n. So, this is also delta. So, if we do this one repeatedly for all the stages also, we will be getting one difference, that is we can say this one, say extract minus raffinate. So, that is we can say this is the delta. So, that delta actually we will be getting here. How to get this one we will be discussing in detail like this. So, since the stages are ideal, so the streams E n and R n leaving the nth stage are in equilibrium. So, we are assuming that all the stages this one we can say this one attain equilibrium before leaving the this one extraction unit. Okay. So, we can say we will start this step by step calculation procedure for this we can say multi-stage counter current extraction unit. This is very simple, very easy to understand also, and so we will be doing this one. Now, we need to draw this one, what I told actually earlier. We need to say, if we know the we can say this extracting solvent, carrier solvent and solute miscibility, then we have this ternary diagram. So, we will be now drawing this one from the we can say the equilibrium data point, we will be getting this we can say binary phase zone by drawing this we can say equilibrium line. So, this one we can say this one, suppose this is the plate point. So, left hand side will be raffinate arm and right hand side will be the extract arm. This is common to every extraction stage like this. So, now we have to draw this ternary equilibrium diagram. So, first step will be like this, we need to draw this ternary equilibrium diagram. So, this diagram may be of any type, say what we discussed this one, it may be right angular triangular diagram, it may be equilateral triangular diagram, it may be solvent free basis also. So, whatever will be this one, but for most of the this one calculations we prefer this right angular triangular diagram for convenience. We will be also discussing this one while we will solve the problem. This is a very convenient way of this one drawing this right angular triangular diagram. Okay. Then we need to locate we can say this point feed point as well as this solvent point. So, this feed point, that is composition is already given, how much amount of the solute is there. Suppose in this case, suppose around 45% solute is present in the feed. So, it is like this Xc will be 0.45, whereas this we can say this one Xb will be 0. Okay. So, this is the feed point, and the solvent point this we can say this one, that is S will be almost say we can say this one pure, or some amount of the small amount of the solute may be present. Based on that actually it will be placing near to this we can say this one in the Xp and Yb axis. Okay. If it is 100% pure, then it will be touching this y axis where y axis is equal to 0, and if the ys is not 0, then it will shift towards the we can say this one this following this equilibrium diagram. So, maybe somewhere here like this. Okay. Now, we need to get this one, this we need to add this F and S. So, we will be adding this one. Now, we will be getting this point M. So, M will be located. Now, we say we need to locate M, that is the mixture point. So, this mixture means if we know M, then from the component balance we will be getting suppose this x m. So, from there we will be getting this M. Okay. So, this now we need to calculate this, the second step will be like this, we need to calculate x m from this component balance like this. We will be doing this F x f plus S y s by F plus S. So, if we know all these, because you see this x f and y s, these are already given in the problem, means that this one, what is the feed, we know this one, and what is the solute concentration in the feed and the solvent flow rate, and then we can say this one total amount of feed plus solvent. So, we will be getting now this x m. Okay. So, then the third stage will be like this. If the solute concentration at the raffinate of the final stage is known, like this we can say this one, if x n, that is we can say this one solute concentration of raffinate, that is leaving the last stage actually, raffinate of nth stage, or we can say this one nth stage, or that is the final stage is known. Suppose this is given as this known parameter, then we can say this one, say R n and m are joined like this, that is if it is given, then we can say this one in the raffinate whatever the solute concentration, suppose x n is given. So, it will be like this somewhere else, then we can say this one, we have this R n is known, suppose then x n is known, then we will be adding this R n and joining m, then we will be extending to the extract arm, then we will be getting this E 1. Okay. So, now we will be join suppose R n and say and m, then extend this one, extend the line to E 1, that is now in the we can say the extract arm. Okay. Now, we have this one f is available, we know then E 1. So, we know that this the difference point actually that we found out that suppose E 1 minus f or s minus R n, that is giving this delta. So, we can say this one whenever we have this f and E 1 we have this one. So, we can say this one E 1 minus f, or we will be getting now say s minus R n, suppose we have this s and R n. So, from there we will be getting this same delta. Like this, now we have this E 1 and f, suppose we will be joining one line, we have R n and s. So, from this we can say this one s minus R n or E 1 minus f, where it will be meeting. So, that is nothing but delta. Okay. So, from there actually we will be getting this, we can say this, from there we will be getting this difference point. So, if we extend f E 1 and R n s, then we will be going to this difference point, like difference point. So, this delta. So, we will be getting this delta. So, for all these stages also, if we extend this one, it will meet a particular point, that is called say difference point is, that is delta. Okay. Now, the fourth stage will be like this, say draw the tie line, that is just like this one whatever we have done in the other, we can say this one extraction processes. So, we need to draw tie line, this one through E 1 and R 1, like this we will be doing this one. So, we have now this one, say we can say E 1, we have this, if we get this we can say this one tie line. So, we will be getting R 1. Now, drawing this one like this, from here we will be drawing this equilibrium line, a tie line. Here we will be getting this R 1. Okay. So, this is the tie line, then we will be getting this R 1 here. Okay. Whenever this R 1 we have this one, it is nothing but the whatever raffinate is obtained from the stage 1, that is nothing but the feed to the stage 2. Okay. And now, we have this delta. So, if we do this one, if we repeat this one, we can say this one, say the stage 5 will be like this. Now, we have this delta point we have, suppose this is R 1 we have this one, because this is the tie line from E 1, and then we can say this R 1 and delta. So, these two are added. Now, we will be getting this E2 here. Okay. So, then we will be obtaining this, then if these are added, then we will be getting E2 in the extract arm. Okay. So, that will be, we can say this one. Now, again this from this we can say this we need to draw this, suppose this stage 6 will be say from E2, again we will be drawing the tie line, then it will be like R2. So, now what we will be doing this we can say tie line through this E2 meets R2 in raffinate arm. Okay. So, this is R2, that is the feed to the stage 3. Okay. So, now we will be continuing this one, suppose this again we will be adding this R2 and delta. So, here it will be meeting E3, then we have again this we can say tie line, we will be getting this R3, and that way we will be actually continuing. Okay. And then we will be getting say one time we will be reaching like this. So, whenever we have this R3 we will be joining with delta, then we will be getting say now say E4, then from there we have this we can say tie line, there we will be getting say R4. So, that way again we will be drawing this tie line, and then we will be getting E5, and then suppose we have this again tie line, we will be getting suppose R5, then we will be adding this one. So, one time we will reach, actually we will be now we can say this one, we will be now continuing this one, continue this procedure till Rn is obtained or reached. Okay. So, this is one this one route, actually this is we can say the very convenient route. I think we are able to understand the procedure for the stage calculation in the counter current extraction process. So, another the alternative technique is there, like this we can say this one alternative technique. So, what we will be doing, a line drawn from the difference point delta intersects extract arm at point actually E n plus 1, and at raffinate arm this extract arm that is in n plus 1 and raffinate arm at Rn. Okay. Now, we can say this one, then second stage will be the location point like this, we can say this one xc and yc plus 1, that is nothing but the is operating line. That is on, suppose it is xc and yc plane. We will be drawing this one xc yc plane also, we will be drawing this one. Then we can say, then a set of xc and yc values are derived to draw operating line. Okay. So, that also we can do this one. So, we can say these in the using this alternative technique also we will be doing this, we can say counter current multistage extraction system. Now, we have this another system, that is we can say this one continuous counter current extraction with some reflux. This is we can say this one the solute concentration in the extract leaving a counter current cascade can at best be nearly at equilibrium with the feed stream. So, it is possible to have a richer extract by the use of the reflux at the product end of the cascade. This system is similar to that of the distillation unit. So, this is the feed point location. So, feed is adding here in the fth stage, and then say this one we can remember that we can this equivalent make this equivalent like this. Say this raffinate from this fth stage will follow this route, means and then we will be getting the final raffinate from the last stage or nth stage, where the we can say this one extracting solvent was added. Like this is counter current operation, but feed is not added at the stage 1. This is added to some extent in between like this. So, to increase the we can say extraction efficiency also, and the suppose extracting solvent is added in the nth stage. So, this part is common. So, we can say this one that raffinate stripping section is common. The feed is added in between this we can say this one stages, and after that say again say suppose this extract will be following this route, and then say whatever the we can say this one another feed, or we can say this one whatever R 0 we can say, that is added in the first stage. That is nothing but another raffinate actually which that is coming, or we can say this one first stage. Some of the part actually is taken out as the product. If the situation demands like this, say if we get the time also we can explain this one. So, in that case we can say this one the reflux will be like this R 0 minus this P E, whatever the product actually we are extracting, then the difference is entering here like this one. This is the we can say this one whatever reflux is added here. So, that is coming as the feed to the stage 1. Okay. So, this is R 0 minus P E, that is we can say this one, because R 0 we have obtained from the separator of any of the system like this, where the extracting solvent actually is separated, and some amount of this we can say this extracting say what is called that carrier solvent, or we can say this one anyway if it is a feed, some amount of is taken out. So, we can say this one, this is nothing but the reflux. Okay. So, we will be discussing about the liquid extraction equipment like this. So, commercial extractors are of like this, generally two types like this classification based on the agitation inside this extraction unit, and we know this one also. The extraction units are mainly consisted of two different types of equipments like this. One is this mixer, another is the settler. So, we can see this type of agitation. Based on that we have three different: unagitated, pulsed column and mechanically agitated column. And phase contact by the centrifugal force like this, then we can say this one centrifugal contactor, then paid by Liang and a few other also are there like this, we can say Robatel, then Delaval. These are the different names of the extraction units. Then like say this one unagitated column, there are spray column, then packed column, then we can say perforated plate or sieve trays are there. So, based on the pulsed we can say agitation, we can say this one is this pulsed, then one is the packed column, and this sieve tray also is there. And during this mechanical agitation, using this mechanical agitation, one is the rotary agitated contactors are there, then Sibel columns are there. These are under the after the name of the scientist like this, and then old Suraston column also. Then rotating disc column, we can use this one rotating disc column in a wide range in case of this extraction. Another is the Cooney column also, this is the after the name of the scientist, and another one is also reciprocating plate column, like this perforated plate or zinc plate also are there. Now, say these are the, we can say this one, whatever the extraction units are there, we can now this categorize like this. We can say in general, we can say this one mixer settler, like this mixer may be there, settler may be there, or tower extraction units are there also. There are also centrifugal extractors, then unagitated, like this, whatever we have discussed in the previous slide. Now again we are this one categorizing this, like spray tower, packed extraction column, sieve tray, pulsed, then using this rotary agitated extraction column like this Siebel, then also Ruston, then Cooney. The another one is the car column, this rotating disc contactor. I told that this is widely used in the different industries. Okay. So, thank you. So, in the next class we will be discussing about the design calculation of multi-stage counter current extraction.